The graph of the cubic parent function, y equals x cubed, remember it looks kind of like an S. I'm going to fill out the table. I'm going to use my normal table values, which are -2 to +2. And if you plugged in -2 cubed, it would give you -8. -1 cubed is -1. 0 cubed is 1. 0 cubed is 0. 1 cubed is 1, and 2 cubed is 8. So it's similar to quadratics where you have the same numbers, but now they're opposite signs. And that's kind of what makes it look like a parabola where one side is flipped upside down. So I'm going to graph these. So here's -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. So this is what the graph looks like for the parent function. And now we need to talk about these key things that go along with each family. So the domain is all real numbers, meaning that if you follow this graph to the left and to the right, it would keep getting wider forever and ever, and therefore cover all of the x values. The range is actually the same, it's all real numbers, and these two things will always be true of every cubic function. End behavior. Remember that we always need x going to infinity and -infinity. So if you imagine yourself on a little roller coaster here on the parent function, if you follow this graph to the right, it's also going up. So that means as x goes to infinity, y goes to +infinity. And if you follow this graph to the left, it's going down. So that means as y goes to -infinity, so does y. Now there's a bonus feature. We talked about the vertex of a parabola. Cubic function does not have a vertex, but it does have what we call an inflection point, or a point of inflection. And that's what happens kind of in the middle of the graph. And I know that's not a great explanation, but this point right here that I'm making purple, right at 0, 0, that is the point of inflection of this graph. And the way I like to think of it is it's like the turning point of the graph. So if you were on this roller coaster and you were all the way down here where I just drew this purple star, as you go up the graph, you're kind of going up and over, and then when you get to this point, now you're going kind of like down and up. So it's a turning point. It's like the swivel points that I guess you could say on the graph. But usually you can get to it just by looking at it. And again, on your table, it's not obvious, but it's that middle point. I know that these other pairs of points aren't exactly the same. They have opposite signs, but they do have a kind of a partner or a pair that looks like the same number. So the first thing I like to do in these is I like to identify my point of inflection. So I can see that it's right here. It's kind of where the graph flattens out as it goes to curve again. So this is at the point 1, 3. So I'm going to go ahead and label point of inflection, and what this does is it helps me figure out my translation. So normally the point of inflection is at 0, 0. So this tells me that my graph went to the right 1 and then it went up 3 to get to the new graph. So I'm going to go ahead and put down right 1, up 3 as part of my transformation. Now I do need to check to make sure that it isn't reflected, and it is not. Over on the left here, I'm going to draw a picture of what the parent function looks like. So you can see that this one goes up to the right, just like the parent function does over here. So that means it is not reflected. And then to find that a number, we're going to do the same thing that we did with quadratics, where we're going to go from the point of inflection, we're going to go right 1 and then up however many it takes us to get to the graph. So this tells me that my a value is 1. Which is not different from the parent function. That means we don't have to list it in our transformations. So now I can skip to my equation. I don't have a negative because it's not reflected. I don't have an a value that I need to write because it's 1, which is the same as the parent function. So now I can go straight to, it goes right 1, so I'm going to use x minus 1, and then up 3. For my domain and range, Remember that for all cubics, both domain and range will be all real numbers. And then the only thing left to do is end behavior. As x goes to the right, my graph goes up. So I want positive infinity. And as x goes to the left, my graph goes down. So I want negative infinity. For example 2, I want to identify my point of inflection, which is right here. So that's at the point -2, -3. The transformations then are telling me that it's going left 2 and down 3. And now I want to take a look. If you notice that this graph goes up to the left and the apparent function goes up to the right. What that means is that this graph has been reflected. And we'll notice that when we do our A value, if I start at my point of inflection and I go to the right 1, it takes me down 2 to get to the graph. So what that means is that not only is my A value 2, it's a -2 since I had to go down to get to the graph. So it's reflected and it's also got a vertical stretch. And I know it's a stretch and not a shrink because 2 is bigger than 1. So my equation is then going to look like this. Negative for the reflection, 2 for the vertical stretch, x plus 2 since this graph is going left 2, and then -3 for down 3. Domain and range are easy today, all real numbers. And then my end behavior, as x goes to the right, my graph is going down. So it's going to go to negative infinity. And then as x goes to the left, my y values are going up towards positive infinity. The first thing that I want to do here is identify my point of inflection. So I'm going to write the general formula up here. The point of inflection is going to be hk, just like it was the vertex for quadratics. So remember that your h number is going to be the opposite sign, that is. And then I'm going to put a little star over here. If you are missing either h or k, you plug in a 0 in its place. So over here, this is my h value, and then my k value is missing. So what that means is it's really like an invisible +0. So that's going to be my point of inflection, will be +1, 0. That goes in the middle of my table. And then I'm going to use my calculator. I'm going to put in the function, and then you're going to use the table function to fill in the rest of our table here. So now I'm going to plot these points. -1, 8, 0, 1, 1, 0, 2, -1, and 3, -8. So here's my graph. My point of inflection, I already know, was 1, 0. That was the first thing we identified. Domain and range of every cubic are all real numbers. This one asks for X-intercept and Y-intercept, and it's only going to ask you that when you have nice even numbers where it goes through at whole numbers. X-intercept is talking about where this graph crosses through the x-axis. So that would be this point right here. And that's the point 1, 0. Y-intercept is where this graph crosses the y-axis, and that is at the point 0, 1. And then lastly, end behavior. As x goes to the right, y is going down, so towards negative infinity. And as x goes to the left, my y values are going up towards positive infinity. First thing I would like to do is identify my point of inflection. So that's going to be -2, -1. So take the opposite of your h value and take the same as your k value. That's going to be in the middle of my table. And then I'm going to use my calculator to figure out the rest of the values, which are -9, -2, 0, and 7. And remember that from your point of inflection, you're always taking the two points below and the 2 points above that point when you go find that on your table. So now we're going to plot these points. -4, -9 would be here. -3, -2, -2, -1, -1, 0, and 0, 7. I missed some points there, but you get the idea. Domain and range are always all real numbers. Point of inflection was something we identified right off the bat, -2, -1. And then end behavior, as x goes to the right, y goes up, so that's positive infinity. As x goes to the left, y goes down towards negative infinity. Point of inflection here is actually 0, 0. So I'm going to rewrite this equation so you can see what I'm talking about. This is really like saying x minus 0 cubed and then plus 0. So my h is 0 and k is also 0. So in the middle of my table is going to be 0, 0. And then we're going to plug in other numbers. We're going to plug in the equation to get the other numbers. And that will complete our table. Now 16 for the y values is not going to fit on our graph. So I'm going to scale my graph by 2's. So every box is going to be worth 2. So if I'm going left 2, I'm actually going to go left 1 box, and then I'm going to go down 8 boxes, and that would really be -2, -16. -1, -2 would be left half a box, and then down a whole box. 0, 0, 1, 2, and then 2, 16. Okay, domain and range, as always, all real numbers. Point of inflection is 0, 0. X-intercept is talking about where this crosses the x-axis, which is right here. So that's at 0, 0. And then y-intercept is actually the same point because it's where it crosses both axes at the same time. And then end behavior, as my x goes to the right, y goes up. And as x goes to the left, y goes down. Point of inflection here would be -1, +2. So that's going to go in the middle of my table. And then you're going to put that into your calculator so that your table function can figure out the rest of your points for you. So I have -3, 10, -2, 3, 0, 1, and 1, -6 to complete my table. This one I'm not going to scale because it only goes off the graph by 1. So I'm going to go to -3, 10. It would actually be up here, kind of off the graph. -2, 3. -1, 2. 0, 1. And then 1, -6. Okay, so now I'm going to connect the dots. And now we can answer these questions. Domain and range are all real numbers. Point of inflection we discussed is -1, 2. And then the end behavior, as x goes to the right, y is going down. And as x goes to the left, y is going up.